Thank you. All right. Part A, you're just checking bins. So B, binary, there's only two categories, success and failure. Success, they visit at least once a month. Failure, they don't. Independent, that's the weird one. Remember, a lot of times it'll say it in there. If it doesn't say it in there, we just assume. So in this case, it doesn't specifically say they're independent, so we just assume that they are. And the number of trials is 500. Probability of success is 0.5. So then on B, you have to check the conditions for using normal approximation. The two conditions are n times p is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. Since p is 0.5, they end up being the same, and you get 250 for both of them. Then on part C, you had to find the probability that at least 235 of the men in the sample visit an online auction site at least once a month. So the probability that x is greater than or equal to 235 is equal to 1 minus the probability x is less than or equal to 234. Because binom CDF only tells you the left-hand side. It's not like our normal CDF where we can set it up to do either side. Binom CDF only does the left. So then number of trials, probability of success, and the x value we're interested in. And when she plugs that in, you get 0.0828. And then she subtracted from 1, which is 0.9172. Now, technically, I wanted you guys to use normal CDF. That's why it says the normal approximation. So Jillian's going to come show us how to do it with normal CDF. Say that again. Thanks, ma'am. All right, so on this one, I'm going to add a little to what she gave us. Anytime we use normal CDF, we want to think about a normal curve, right? So here's our normal curve. From last time, we know the mean is found by taking n times p, and the standard deviation comes from n times p times 1 minus p, and then square rooting it. N minus p We know from part B is 250. And then if we do 500 times 0.5 times 0.5 and then square root it. I could have sworn I had a calculator. So n times p times 1 minus p is 125, and then, oops, wrong button, sorry. And then we're going to square root 125, and we get 11.18. So our standard deviation is just over 11, which is what she had here for her standard deviation and her mean. I'm just adding the picture. So we have 250 at the middle here. That'd be 261.18. I'm not going to label those because that requires my brain doing more math. Minus 11 would be 39, so 238.89. 82, excuse me. I did 11 twice. So 235 is what we're interested in, and at least 235 is greater than. So I'd say 235 is around here-ish. And we want to know greater than or equal to, which is why Jillian put 235 as the lower bound. Big number for the upper bound means standard deviation. And notice that Hannah's answer using binom CDF and Jillian's answer using normal CDF are very close. Questions? Hey.
So when we were doing bins, I don't understand S, probability of success. How is that 0.5? Are we just saying because there's only 2 options?
It says half of male internet users in the age group visit an auction site. And half is 0.5.
Okay, so we're taking that as a given, but then what are we calculating? Whether or not the sample matches that statement? Because I thought we were trying to prove that half the male users.
I wouldn't say you're trying to prove.
Okay.
You have a sample, and it showed that half of the male internet users visit an auction site. And then if we take, let's say, it doesn't specify, but let's say we're looking at the whole population, which obviously we can't. And they keep track of internet sites and who goes where. So they do have access to a lot of information. So they could find that about half of 18 to 34-year-old males go to eBay once a month. And then we randomly pick 500 of them. Would it still hold true?
Okay.
Any other questions? So today we're going to look at geometric random variables. So last time in the video we talked about the starburst and looking at cherry flavored starburst. We're going to build on that idea and we're going to work with starburst again, not till towards the end, but we are going to be working with starburst. And yes, I did bring you starburst. Usually I bring it with the last lesson, but since I wasn't here, I have starburst for you today. All right. So first thing we want to do is define some geometric variables. So a geometric variable x is the count of the number of trials needed to obtain one success. X can take the values 1, 2, 3, 4, and on until you get to X, and X includes the trial that is a success. So some examples would be the number of times I flip a coin until I get a heads. Or the number of times I have to roll a die until I get a 3. Or the number of kids until you have a girl. Or how many times you have to shoot a free throw until you make one. Those are all examples of geometric variables. Of course, there are a ton more out there. I'm going to abbreviate free throw as FP. So with geometric variables, we have to check the geometric setting. It's very similar to binomial. Instead of bins, it's bits. So B is the same. Binary, you have every observation falls into one of just 2 categories, which are success and failure. Then we have, excuse me, I, independent. So knowing the outcome of one has no effect on the outcome of the next. And then this is where it changes. Instead of N, it's T. It still is talking about the number of trials, but with a binomial setting, the number of trials is fixed. So like in the warm-up, we looked at a sample of 500. Here with geometric, we count the number of trials until the first success. So it's not a fixed number of trials. And that is the only difference. So you might want to put a star next to it. The B, the I, and the S, they're all the same. Nate?
Yeah, what's wrong with that?
I don't care. Last S, success, probability of success. P is the same for each trial. So the only thing that is different between binomial and geometric is the number of trials. Binomial is a set number. We don't go past that number of trials. Geometric, we keep going until we get that first success, and then we stop. So like a coin toss, if a success is heads, it may be that we get our first success on the first flip, and we get heads right away, and then we're done. Where with binomial, we would look at how many heads we get in 50 tosses. So I just said that without writing anything. The main difference is number of trials is not fixed. Or geometric. Not fixed or geometric. So we're going to work with the idea of rolling a die until we get a 3. Can I move up my paper?
Yes.
Thanks. So we're going to roll a number cube, not a dice. By the way, I know it's die. I'm going to say dice because that just comes out easier. Die just sounds weird. So I know I'm wrong, but I'm going to say it anyways. So we roll a die, and we have X represent the number of rolls until a 3 occurs. First thing we're going to check is that it's a geometric setting. So we're going to check bits. So B, that's binary. Success is we get a 3. Failure is anything but a 3. So 1, 2, 4, 5, 6. I, independent. So rolling a die, whether I get a 3 or not, on that first roll is not going to change the outcome of whether I get a 3 or not on the next roll. So that's independent. Just say yes. N, number of trials. So we're going to go until a 3 occurs. So there is no set number of trials. So T, we're going to go until we get a 3. Or you could say N is not fixed, however you want to word it. And then S, probability of success. Oops, sorry. There we go. What is the probability we roll a 3? 1 out of 6. And that stays the same every time I roll the die. Yes, sir?
What's not fixed?
I'm going to keep rolling the die until I get a 3. So it could take 1 roll, it could take 3 rolls, it could take 100 rolls, because I can't really know how many times it'll take before I roll a 3. And it could be different each time I do this experiment. Sometimes it could take 5, the next time it could take 1. So, probability X equals 1, that's finding the probability that I roll a 3 right away. So it only takes 1 roll to roll a 3. So in words, getting a success on the first roll. So what's the probability I get a 3? 1 out of 6. So the probability that I get a 3 on that first roll is 1 out of 6. So the probability X equals 1 is just 1 out of 6. Oops, I put my, sorry, I don't know why I closed the parenthesis right away. It was not what I meant to do. So then the probability x equals 2. So I get a failure on my first roll, and then I get a 3, a success. So this is fail and then success. So what is the probability I get something other than a 3? 5 out of 6. And because of the independence, I can multiply my probabilities. And then the probability I get a 3 is 1 out of 6. So the probability that it takes 2 rolls to get a 3 would be 5 6 times 1/6, which is 0.139 if I round. So what's the probability I have to roll the dice 3 times before I get a 3? That would be fail, fail, then a success. So the probability of failure is what? 5 out of 6, and then I get another failure, so 5 out of 6 again, and then I get a success. I don't know what is going on with my brain. 1 out of 30. Sorry. I multiplied 6 times 6, and I didn't want to yet. Goodness gracious. 1 divided by 6. There we go. So 5 6 times 5 6 times 1/6. We get 0.116 when I round. Anybody notice a pattern that might help us generalize this to a formula? So when x equals 1, that was just getting a success right away. Here, 2, we had a failure, then a success. 3, fail, fail, success. So if it takes n number of rolls to get a success, that means I failed 1 less than n times. So the probability that x equals n is going to be the probability of failure, which in this case is 5 6, to the n minus 1 power. Because here we had 2 failures, so really I could have done 5 6 squared, right? Which is 1 less than the x value we're interested in. And then I'm going to multiply by the probability of success. Now I'm going until I get the first success, so I don't raise that to any exponent. Right here, n minus 1. Now, for some reason, the AP formula sheet doesn't use n, they use k. So down below, I'm going to show you what it looks like on the AP formula sheet. So if we're working with a geometric distribution, p is the probability of success. That means 1 minus p is the probability of failure. And we want to find the probability the first success is on the kth trial. We would have probability of failure raised to the k minus 1 power. And then it would be multiplied by the probability of success. And we only have 1 success, so it's raised to the first power, which we don't actually show. Questions? All right, Okay, now we're going to play a guessing game, so you guys can help me. I don't think you meant that yay. The way you said it sounded really sarcastic. All right. You're my first contestant then. So we're going to make a guess at the mean for the following geometric random variables. X is the number of tosses of a coin that we need to get a heads. First of all, what's the probability of success getting a heads? 50-50 or 0.5, 1 out of 2, however you want to think about it. So, if we were to do a bunch of trials, how many times do you think you'd have to toss the coin until you get a heads? 100? Wow. I think your coin might not be fair if you're getting 99 tails. 6? What makes you think 6? You don't know.
50-50.
Okay, so how many trials should it take? 2. 2.
But
2.
what if it's 50-50?
Because either I'm going to get heads first and then a tails, or a tails and then a heads, right? I could get a heads. But on average, it should only take 2 trials because the probability of getting a heads is 1 in 2. So it should only take 2 trials. Now, the formula is, well, hold on. Maybe one of you will get it. This time, X is the number of throws of a die until we get a 2. So what's the probability of getting a 2 when you roll a die? 1/6. So how many rolls do you think it would take on average to get a 2? 6. I don't know why I stopped midway through my mew there. Anybody want to take a guess at the formula we're working with? This one's not quite as easy as last time, where it was just n times p. Say that again? No, it doesn't involve k, it just involves p. Yes. Yeah. Uh-huh. When did that become a saying? One of my other classes asked me that the other day, too. Do I give off the vibe of a P pusher? Seriously, one of my other classes did ask me if I pushed P the other day. I was like, what? All right. Nobody? What if I write the probability of getting a heads as 1 out of 2? And the mean is 2. 1 out of 6, the mean is 6. Anybody see a pattern there?
Yeah.
Hannah?
It's just the amount of times things it could do. Like, is it 1/2 the bottom of the
What is that called in math when we... You had your hand up? No?
Flip it.
You flip it.
Reciprocal.
Reciprocal.
Cool, I knew that.
So we take
What's that little cursive thing? Is that
mu.
Mu?
Mu.
It's average on mu?
I feel like you haven't been paying attention to me for 3 months now.
I've been doing it 35.
Mu. It means average.
There's too many.
It's the Greek letter. All right. So to find your average for a geometric variable, you take 1 divided by p, which ends up giving you the reciprocal. If you work with the fraction, which I know you guys don't like fractions, it'd be 1 over 1/2, which ends up giving you 2. Or you could do 1 divided by 0.5 and plug it into the calculator. You get 2.
Oh no.
Here, 1 divided by 1/6. If you type that into the calculator, make sure you put the 1/6 in parentheses, and that'll give you 6. So, in general, P is P. Mu is 1 divided by P, and then just like with binomial, I can't make you guys play a guessing game to figure out the standard deviation formula, so you're just going to have to trust me on this. Standard deviation is the square root of 1 minus P divided by P squared. Now, these formulas and the formulas for a binomial random variable are on the AP formula sheet, so I will give them to you for your test on Thursday. Too many P's?
That's so they're all not pushing.
I'll give you the mean for geometric, standard deviation for geometric. Same with binomial, the mean and the standard deviation formula. That whole n choose k, p to the k minus 1 times 1 minus p to the, that one will be on there too, because that's all on the AP formula sheet. All right, any questions before I get into actually using these formulas? All right, so we're going to go back to Starburst. So we're going to randomly select Starburst candies from a bag until we get a cherry flavored one. We're going to assume that randomly selecting Starburst candies is independent. You do get candy after we do the math. If I give you the candy now, you'd all be eating it and not paying attention to me. I want you to pay attention first.
Gives you incentive.
It does. So,
I don't even know.
say that again, Noah.
I don't know how many flavors there are in Starburst.
In a regular bag, there's 4. Lemon, orange, cherry, pink. Strawberry? All right. Quiet down, please. So you guys are going to do number 1. Check that it meets a geometric setting. And then I also want you to answer number 2. What is N and what is P?
What is cryo?
What was your question, Maddie? Okay. No, tap back in.
I would tell you, but I couldn't.
Can you give me like the textbook definition of geometry? Really?
Fits.
Bro, I don't know.
Check fits.
Oh, great.
Four.
Every single day.
You guys know so little about Starburst. No, there's only 4. You 5 different just like but it's only got 4 in it. Every flavor pack only has 4 flavors.
I normally get like those pink packs, and they all look like really similar. So
Why would you only get the pink one?
because those are the best.
No, the
Yes.
orange ones are the
No, the pink ones are like you get raspberry, cherry, strawberry, and something else with pink. I mean, oranges are kind of just like they don't taste like orange.
What's high? Yes. It's like trial.
Here you can say it's not applicable.
Yeah, it's a code, yes,
What number is cherry?
Maddie's gonna put the answers to 1 and 2 on the board for you.
Oh,
It was fast.
yeah. What is the other thing?
Cherry Yeah, lemon. Thanks, I said cherry. Sorry, Alex. I know what I'm doing.
Is it a strawberry?
Cherry. And orange? There's lots of things. Like she says, on her, she said until first success. Or until first success. Yeah, that's what she wrote. Until first success. Because that's what N is. You just keep going.
Oh my.
Thanks, Maddie. Well, see, you tapped out, so no Starburst for you. I said there's Starburst. Gosh. All right, so geometric, she checked bits over here. Binary, success is getting a cherry, failure is any other flavor. Orange, lemon, and strawberry. It is strawberry. Independent. It tells you up here that we're going to assume independent. So yes, or put the word independent, however you want to say it. T, the number of trials. We go until we get a cherry. And S, the probability of success. There are 4 flavors, so it's 1 out of 4, so 0.25. So we met geometric. Here on N, she put until first success. That's a fine way to say it. Or you could say NA, because it's really not applicable because we don't have a set number of trials. Or you could say N is not fixed. There's not really a certain way you have to say it when you're identifying N. She said until success here. Over here, she said until we get a cherry. That's 2 different ways to say the same thing. And then P is 0.25. So what is the mean of X? How many candies am I going to have to draw out of the bag on average until I get cherry? Nate?
4.
It is 4. Remember, the mean is found by 1 divided by P. And 1 divided by 0.25 is 4. Eric tapped out, so he doesn't get to do it. He gets to do it, and he gave me 4. Jump up.
But they always correct you.
Draw a strawberry. Strawberry. Just one. Let's see if it's cherry. Oh, no.
I do.
Throw it down. Throw it down. Nope.
If he gets all the flavors,
One more.
he gets strawberry.
Oh.
Why?
You got one. Yes, sir. 5 trials.
No.
And I got 3 oranges.
Oranges are the best.
Oranges are okay.
What the?
No.
Orange is not the best.
Orange is the
Orange
best.
is the best. And yellow. And pink. I like
And red.
I hate red. Orange, yellow, pink, bro.
Alright. Quiet back down, please. So, when we interpret, we're going to, remember, say something like, on average, it would take us 4 Starburst candies until we get that first cherry. I'm going to abbreviate average because I'm lazy. Are you writing this, Eric?
I am.
Good job. Maybe, we'll see. All right, on number 4, we're going to find the standard deviation. So up here you can kind of see it, except for my paper moved on me. So to find the standard deviation for a geometric variable, we take the square root of 1 minus p divided by p squared. So we're going to take 1 minus p divided by t squared. So the square root of 1 minus 0.25 divided by 0.25 squared. That is 0.25 squared. It almost looks like 0.252, sorry. Make sure that you do this part before you take the square root. So 1 minus 0.25 is 0.75, and I'm going to divide by 0.25 squared. And then I'm going to take the square root of that, and I get 3.464. Good. I'm glad you see. And what does standard deviation tell us? On average, how much it would vary from the mean. So when Nate drew them, it took him 5 instead of 4. So over a bunch of trials, on average, it would be between the 1st and the 7th candy, but most of the time around 4. Am I off the screen? Just... Yes.
On my calculator it says non-real answer.
So your calculator? See this for division. It did the division.
Who did that?
You have to put the 1 minus 0.25 in parentheses on the parentheses. Otherwise, the calculator will follow PEMDAS. All right. So, just like with binomial random variables, we had a new calculator function, binom PDF and binom CDF. Our calculator has those functions for geometric random variables. So what is the probability of selecting 5 candies to get the first cherry flavored one, like Nate did? So we have an exact X value that we're interested in here. We want to know the probability that we have to select 5 candies. So that's the probability that X equals 5. Now, this one wouldn't be too hard to do by hand. We would take the probability of failure, 0.75, and raise it to the 4th power and then multiply by the probability of success. But I'm going to show you how to do it on the calculator. So this is a PDF because it's exactly equal to 5. So the calculator function is geomet and then PDF. And when you go to this calculator function, the new ones prompt you. the older ones, they expect you to know that you're supposed to give P the probability of success and X the X value you're interested in. So here, the probability of success is 0.25, and we're interested in knowing the probability it takes pulling 5 candies out of the bag until we get that cherry. So it's going to be 0.25, comma 5 for those of you that have the older calculators. This calculator functions the same place as normal CDF and binom CDF. So you're going to hit second bars. You do have to scroll down just like you do with binom. Where is it? Actually, this one might be the one that's easier. Yeah. If you go to this, if you scroll up, it's much quicker because Geomet is the last one. So we're working with Geomet PDF. New calculator prompts you. So P is 0.25. I'm interested in X equaling 5. And then I'm going to paste. And we get... no, seats have not changed. I just gave yours away because you weren't here. 0.0791. You're fine. Just stay there. He can find the new seat. Uh-huh. So probability that it takes 5 candies until we get that first cherry is 0.0791, or about 8% of the time. Yes. So on number 6, it says, what's the probability of selecting at least 5 candies? So the at least part tells us that we're going to work with Geomet CDF. At least 5 is greater than or equal to 5. And just like binom, Geomet only tells you the left side. And this is asking for everything to the right of 5, so you have to do 1 minus the probability that X is less than or equal to 4. And let's just put a little note. Binom CDF and Geomet CDF only tell you the less than. So you have to subtract from 1 if you're doing greater than. So we would do 1 minus Geomet CDF. And probability of success, 0.25, and the X value we're interested in is 4. Were you saying no to me? No. Okay. Second bars, scroll up, Geomet CDF, so 0.25, X is 4. And then I'm going to subtract that answer from 1. So I get 0.3164. So with 1 minus 0.6836. So probability that X is greater than or equal to 5 is equal to 0.3164. Sorry. Zoom out a little. There we go. Any questions? No? All Alright, so I'm gonna have you guys try the exit task. And while you're working on the exit task, I'll come around and let you have some candy.